All right, so these here you have just some of my notes, okay? And I'll put these on Blackboard. Remember, my notes have to guide me in what I should talk about and what's important. So you need to know more than just what's in my notes, okay? So then don't ignore the textbook and just read all of these and be able to write these. You need to be able to explain them and say a lot more than I have there, okay? So we want to talk about effects of temperature fluctuations, right? And as we saw before, once we increase temperature, we kind of increase the efficiency of the atomization process, meaning as temperature goes up, more of the sample gets atomized, right? And therefore the number of atoms in the vapor changes. And if the number of atoms in the vapor changes, that's the equivalent to using a bigger cuvette, because now the light, as it passes through the flame, all right, or whichever atomization technique you're using, as it passes through, the concentration of analyte changes. So therefore you get a error in the, or you get fluctuations in the reading. All right, we get line broadening. All right, and we can have decrease in peak height due to the particles traveling at different rates. Also remember, we spoke a little bit about the Doppler effect, and the Doppler effect is really very important and very exciting, because as far as you're concerned now, whenever you make a measurement, you have confidence in the measurement, right? Because the instrument that you are using to make the measurement doesn't impact what the output is. So if you put a thermometer in a jar with ice water, you get a reading, and that's fine. When we get atomic spectroscopy, we see something called the Doppler effect. Well, the Doppler effect works in atomic spectroscopy. And what it says is that the relationship between what is being measured and what is doing the measuring, right, changes depending upon the orientation of the two. Right? So it in effect says the act of measuring something changes what is being measured. Right? And in the Doppler effect, you hear the Doppler effect. If you're standing on Georgia Avenue and you hear the siren coming up, your ear is the detector, right? And the source is the siren, is what's coming up on the ambulance, right? And you hear that sound. And as you come up, all right, the pitch increases. Not the volume, but the pitch. It goes to a higher pitch, because the relationship between the source, which is that fire engine, and your air changes as it comes up. So the frequency increases, and as it goes further apart from you, the frequency decreases, right? So if you stand up there, you hear the difference and you recognize it. It becomes sharper as it comes to you, and then it decreases, right? So that, in effect, just measuring something changes what is being measured. And that's one of the problems, that's one of the errors in atomic spectroscopy, right? And that produces line broadening, because ideally we want, we ideally don't want, we ideally want this, right? But we still get something that looks like that. This bandwidth is extremely narrow, but we still get something like that, right? All right, and that's the Doppler effect here, which is enhanced. It increases the degree of ionization of the analyte, right? So if temperature increases the degree of ionization of the analyte, then, you know, the ratio between non-ionized sample and ionized sample changes, and then we get some problems with the measurements. Let's look at atomization methods, okay? When we talk about atomization methods, something should come into your mind. That is, how are we going to convert our sample from whatever form it's in, whether it's a solid or a liquid, how are we going to get it into atoms, right? Because we're doing atomic spectroscopy. When we did molecular spectroscopy, we didn't have to worry about getting it into molecules, right? We just put our sample in solution in molecular form, and we're fine, right? So atomization is important because that's of all the processes involved, that is the one that determines the precision and accuracy of the method that we're using, right? So this step of atomization and how the sample is introduced is really important, all right? And just to note here, that's the step, this is the step that limits the accuracy, precision, and detection limit of the technique. Our ability to always have a representative and consistent sample interacting with the flame if we're doing flame spectroscopy, right? And what we said before, that what do we want with sample introduction? To produce a reproducible and representative portion of the sample into the atomizer. Remember, when we talk about atomizers, what comes to your mind? Atomizers would be the flame, electrothermal, laser ablation, arc and spark, all right? So those are the atomization methods that we will talk about, right? All right? And we're saying here for liquids and gases, it's easy to atomize, right? This step is easy, but when we get to solid samples, we have problems. Because remember when we looked at solid, when we talked about arc and spark, right? We're producing this vapor cloud, but it doesn't have a uniform particle size, all right? So that it means that at some point the detector might be getting more sample at another point. And that's why most of atomic spectroscopy is done in just liquids, all right? All right, we see solid samples are problematic. And here we should remember this, we have two types of atomization devices, right? And we hinted at that, right? One is continuous. We start with nothing, it goes up to some value, and it's continuous, right? That's fine. Right? And in continuous, to have a continuous output means that we must be constantly aspirating sample into the flame or whatever else we're looking at, right? If we want, the other option is discrete, where we get, like that, where we get, we start with nothing and it climbs, it stays there, and it drops like that, right? All right, so in the flame, we have a steady flow of matter, right? In discrete, the sample comes in discontinuous, that's this, right? The amount of it changes, it gets to some plateau, and then it decreases. It increases, decreases. And that happens because you kind of use up the sample in some cases. Or if you're applying an arc and spark, you're not continually applying an arc and spark. You apply a potential, you vaporize some of the sample, you get this, and then you're done, right? All right, we looked at nebulization, right? And the nebulizer constantly introduces the sample in the form of fine spray or droplets. Remember when we looked at that diagram, we had the nebulizer, okay, in the instrument itself, where we had the flame at one end, and we created these droplets. And remember we had the baffles that would discriminate, right? So we'd start with a wide range of droplet sizes, and the baffles would bring it down to a very narrow or small range of diameters, right? And we have the pneumatic nebulizer, all right? And we looked at that, it's drawn through the capillary tube. That's the diagram we saw before, all right? The high pressure of steam, stream of gas. This breaks it up into droplets. We have varying sizes of the droplets, and then remember we have the baffles which produce a uniform sound. Ultrasonic nebulizer, you know what ultrasonic is? You see it sometimes we have a small one if you want to clean jewelry and that kind of stuff. All right, we can have this sample on a piezoelectric crystal. It vibrates at a high frequency. And this produces a more kind of homogeneous aerosol than the pneumatic nebulizer. We know electrothermal, we've been talking about them all day, so I don't think I need to say anything much about that. We use hydride generation for these specific arsenic, antimony, tin, selenium, bismuth, right? And we want better detection. We want a better detection limit. You can read more of this if you want. We know solid samples, how we get solid samples in. All right, hold on. Right, we know this one, we know electrothermal, we know arc and spark. This is just kind of putting down what we've said before. All right, slurry nebulization. We get this finely divided solid sample. It's transmitted into the atomizers and aerosol. And what we have here is a suspension of a solid in a liquid medium. Right? What do we mean by performance characteristics? Performance characteristics, people. And so performance characteristics that we looked at before is just what are the criteria that we would use to evaluate a technique, right? So the example that should come to your mind when you talk about performance characteristics is always your cell phone, right? You use performance characteristics when you want to buy a cell phone, right? You say you want a cell phone with a really good camera, right? So you can take out pictures in low light and high light, so then you have a good resolution, it doesn't come out blurry, all right? So that you've listed performance characteristics there, right? I can, right? So the same thing we use, what are the criteria we would use to compare different atomization techniques, right? So performance characteristics for flame is the most reproducible, right? The disadvantage is that it has low sample efficiency. Remember when we aspirated it up, the baffles reject most of the sample. So in effect, in flame atomizers, over 90% of your sample is in that bottle that you see below the instrument. Right? Just a really, really small percentage. I would guess less than 1% of what the sample actually goes into the flame, right? So the sample efficiency is low, and the sensitivity is low, right? And the reason is that most of the sample does not end up in the flame, right? That's one. The second thing is, if you remember the instrument, right? And I'm just drawing a little piece of the instrument. If you remember that's the flame, right? And then when we have the flame there, we have the source coming through the flame, right? And then from here, we go to the detector, right? Remember that guy? And then your sample is aspirating into the flame. You have your sample in a beaker here, and it's aspirating into the flame like that, right? And it's somehow going up here, right? So we can understand the fact that most of the sample goes down the drain, right? Because it comes in here, it sucks in here, and then there's another tube here where all of it comes down, right? Into a big bottle, right? So that's fine. Most of the sample goes in, right? But what is this idea of short resident time of individual atoms? What does that mean? You say there's a short resident time of individual atoms in the flame. And that's something like 10 to the minus 4 seconds. So it's really a very short amount of time. And so if you think about the instrument again, what's happening is we have the sample in here, right? Wake up. Right? And the sample comes up in here, it goes here, and then it just vaporizes and goes all the way up, right? So it's not like a cuvette where the sample is in the cuvette and it's in there forever. Light is, the source, radiation from the source is shining across there, but it's only interacting with the sample for this really short period of time, because this is going up really quickly, goes up in there and then it's gone, right? All right? So that the resident time, and what does that mean? Well, there should be time in there, the short resident time of individual atoms in the flame. Right? How long does an atom really get to interact with the radiation from the source. And it's 10 to the minus 4 seconds. It's a really short period of time, right? So that results in low sensitivity. All right, so that's what happens for flame atomizers. For electrothermal, you remember electrothermal? Right? Remember electro, that means some kind of potential, and thermal is heat. All right, so we have some method by which we have two electrodes, we apply a potential across them. Right? We get the spark, it heats up everything, and we atomize the sample. All right? This has greater sensitivity. All right? Because remember what we have in electrothermal, right? In electrothermal, we have a sample here. Let's say the sample is a block. All right? We have some method of applying a potential across it, and it vaporizes all at once. All right? So what happens is we have the sample, and then we create this atomic cloud up here, right? We create that atomic cloud, and then the light goes through the atomic cloud to the detector, right? So far, so good? Right? But this cloud lasts for some period of time, right? It doesn't just, might be a second, might be a little more than a second, but compare that with the sample that's aspirating through the flame as a liquid, right? When we said it's like 10 to the minus 4 seconds or something, right? So that we get a longer time for interaction between the sample and the source radiation, right? This results in enhanced sensitivity, all right? Because the sample is there longer, so the sensitivity is greater. We can detect lower concentrations of the sample, right? It's because the entire sample is atomized instantly, and then it has a greater resident time in the beam of the source, right? Here we said it's a second or more. For the flame, we said it was something like 10 to the minus 4 seconds, all right? So there's a huge difference there, right? So we can get better sensitivity, all right? And what we do, we evaporate the sample, we ash it electrically in some heated graphite tube that we showed before with a current, and we get atomization. This is a reminder to think about what the output signal is, and we know what the output signal is because I just answered that question for you, right? Again, performance characteristics, high sensitivity. We know that. All right? We use a small amount of sample. Look at the detection limits. 10 to the minus 13, or 10 to the minus 10. That's really great. Precision, not as good as the flame. The flame is 1%, and this is 5 to 10%. Remember where this comes from, right? When you're talking about precision, right? In the flame, we have this, the beam is always interacting with a representative sample of the analyte, right? Whereas here, just gets some interaction for a very small period of time, right? All right, it's slow, right? We have to heat the whole thing up so we can evaporate the sample, then cool it down, then put in a new sample. So that's some of the disadvantages. What does the instrumentation look like? We hinted at it before, right? The atomic lines are narrow, right? Look at it. It's 10 to the minus 3 nanometers. Okay? So it's a very narrow beam. Atomic lines are extremely narrow. And we spoke about that, right? The requirement for Bayes' law, all right, is that, the radiation must be narrower than the bandwidth of the transition, right? And we've answered that question. Bayes' law requires a narrow source bandwidth relative to the bandwidth of the absorption band. If this is how narrow the absorption line is, then your source has to be narrower than that. And we looked at this before. We solve it by using hollow cathode lamp, which produces a bandwidth that's narrower than this. Electrode-less discharge, which we talked about before. And the electrode-less discharge has the advantages that it's 1 to 2 times order of magnitude greater than the hollow cathode lamp. We talked about what that is already. We talked about that. Source modulation, remember we hinted at source modulation, which is to modulate is simply to change frequency. If you have studied, if you've played an instrument, then you have an idea of what modulation is. So you can hear someone says, well, I want to change the key that I'm singing this song in. Right? So that means they want to change the frequency. Right? So they want to go to a higher key or a lower frequency. So they want to change the frequency. So that's an example of modulation. Someone says, I cannot sing it in A. Let's go down to C. Right? So that's source modulation. Right? We know the flame emits radiation. We know already most of the radiation is rejected by the monochromator. Blah, blah, blah. So to modulate the output is to just put a frequency dependent on the output, right? And when we modulate, the detector receives 2 types of signals, right? An alternating one from the source and a continuing one from the flame. We spoke about that like half an hour ago, right? So that's the advantage. So in a lot of instruments, you're going to see modulation of the source, right? Because once we modulate the source, it means that in our electronics, we can pull the source out from all the other noise that's there. Because the source has this frequency dependence and all the other noise is random. Right? Most noise is just random, whereas the source has a frequency dependence. So you'd have a lot of noise, but what you'd have is that the noise from your source would have a frequency associated with it. Right? And then we have what is called a lock-in amplifier, and it locks into this frequency, right? And only amplifies that frequency and ignores everything else. So it really is an easy way to tidy up everything else, right? We see here the detector is going to get 2 types of signals, an alternating one and a continuous one. So in the flame, the detector is going to be seeing something like this, and it's only going to be seeing something like that, right? It's going to be seeing a continuous. They won't be separated, the one on top of the other. Just let's have it separated for you to understand it better, right? And what's going to happen is, we're going to lock into this one and ignore that. There's still some of this in there, but that's another issue, right? We've seen before that if we have a continuous source, right? So that the source itself does not have to have a frequency dependence, right? The source, the output from the source, if that's the source, right? Just like the lamp in your house. The output from the source is like that, right? It's continuous, right? So that's the source, that's whatever. But we can take that source and by using a chopper, right? Remember the chopper is, it alternates slices of the pizza. So sometimes when the radiation comes from the source, it's coming here, right? This is spinning. At one point in time, it's going to go here, and it's going to pass right through. Another point in time, this guy is going to be over here, and that's blocking light, okay? So when it gets there, it's going to see nothing. So it's going to be, at the extreme, it's going to see nothing, it's going to see something. It's going to see nothing, it's going to see something. Right? And we can make it so that that looks something. Alright, so for instrumentation, we can have a single beam or we can have a double beam. Right? We looked at single and double beam instruments. We know the advantage of double beam. Right done? That's nice. The advantage of a double beam instrument is simply that we have a reference beam, right, that we can compare the sample with. Okay? I think we are done. Okay? So I know you had a really enjoyable time listening to me talk about this. As I always say, I enjoy teaching it. If you don't enjoy learning it, that's your problem. Okay? So I'm going to send you an email. Okay? This lecture is going to be on Blackboard. The next lecture I'm going to do is going to be on fluorescence, which is really another nice, exciting topic. You might have seen fluorescence before. Fluorescence is if we take a sample, let's say a solution, and we shine one color light on it, the whole sample becomes another color. So we shine blue light on the sample, and the whole sample glows green. Okay? What we're going to do is to figure out, first of all, how that works, and then what type of instrument is required. If you open a fluorimeter, what type of instrument is there? All right, so I know you can't wait, but I'm going to give you a break so that we'll do fluorescence another day. I know you want it right now because you're very excited, but just hold on. So I'll put my notes up. I'll put the PowerPoint slides up. But just remember, my notes, you need to know more than my notes. My notes are just a guide. All right? Since we won't be seeing each other, I'm going to go through the chapters and give you a better sense of what you need to really know. All right? So I'll go to page 1. Let's say I go to page 65. I'll see you need to know, the second chapter, the third, the fourth. You might just need to read the fifth, but you need to know 3, 4, and 5, or 3 and 4, and just have an understanding of fifth. Right? So I'm going to give you some kind of guidance. So I'm going to do a talk on fluorescence. After that, all we have would be some chapters on chromatography. Chromatography is the most common instrumental technique, analytical technique. So there are a lot of resources and there are a lot of talks on chromatography or lectures on chromatography. I have some of my own, but I'm going to go through what's out there on the internet, and then I'm going to pick some and I'm going to email them to you, and then I'll just come and talk over those slides, and we should be ready. Start thinking about the next exam. Okay, the next exam should really be the first week of class. We'd have lectures, and the exam should probably be the Monday after that. So start thinking about it. I'll write out what the rules are for taking the exam, all right, so that we're all on the same page. What's going to happen is I'm going to put the exam on Blackboard, all right, and I'm going to put it to be released at a specific time. And we will always be at the times that are due for lecture. Okay, so you're going to have to be available at the lecture time. You can view the notes whenever you want, but for exams are going to start at 10:10, either on a Monday, a Wednesday, or a Friday, and they're going to end at 11. All right? That's part 1. After the exam, all right, you would see the exam on the questions on Blackboard, and you need to work with a pen and paper and write your answers down. All right? Write your answers on a sheet of paper. All right? When the exam is done at 11:10, use the scanning function on your phone to scan your exam, save it as one file, and email me the file. All right? The exam starts at 10:10, it ends at 11, and you have until 11:10 to get your answers in my email box. Any answers that come after 11:10, I'm not grading them. Any papers that come after that, right? So you have 10 minutes here. Yeah, just scan it and get it to me in 10 minutes, and then I'll grade it. Okay? Talk to you again soon.